Hello everyone, welcome to another video from the tutorial series Aspen Plus Mastery and Certification. My name is Dabish. In the last video, we have learned how to simulate non-kinetic reactors. Non-kinetic reactors were classified as equilibrium-based reactors, including equilibrium reactor and Gibbs reactor. And the second class from the non-kinetic reactor was balance-based reactors, including conversion reactor and the yield reactor. In this video, we will learn how to define reaction kinetics in Aspen Plus and how to simulate continuous stir tank reactor and plug flow reactor. Before hands-on practice, let's have a brief background about the possible reaction kinetics that can be defined in Aspen Plus, and then we will move on to the specific problems of this tutorial video. Aspen Plus has an extensive capability to define a range of reaction kinetics and simulate the kinetic reactions using multiple reactor models. Broadly, the kinetics can be grouped into electrolyte solution chemistry and non-electrolyte reactions. The electrolyte solution chemistry is defined in the properties environment, where the possible reactions are equilibrium-based reactions, salt precipitations, and dissociation reactions. These reactions can be generated while using electrolyte wizard, or alternatively, the electrolyte reactions can be added in the chemistry folder of properties environment. Whereas non-electrolyte reactions are defined in the simulation environment, and there is a range of possible reactions and kinetics that can be defined in the simulation environment, including power law reactions, where power law kinetics as well as equilibrium reactions can be defined, Langmuir-Hinshelwood-Hougen-Watson reactions, where LHHW kinetics as well as equilibrium reactions can be defined. There is another possibility to define a general reaction set that can contain equilibrium reactions, power law reactions, LHHW reactions, or power law reaction kinetics can be customized by adding non-standard terms along with the power law kinetics. Besides, crystallization reactions can be defined for the purpose of batch operation, including the stoichiometry of the crystallization reactions, solubility data, and the kinetics. Fermentation reactions can be defined, including the fermentation species and the corresponding kinetic parameters. Reactions involved in the reactive distillation process can be defined in another set of reactions, including kinetic, equilibrium, and conversion-based reactions, or salt precipitations can be defined. The Aspen polymer enables the definition of a range of possible polymer reactions, including free radical emulsions, free radical polymerization reactions, ionic reactions, polymer pyrolysis reactions, segment-based step growth reactions, and Ziegler-Natta catalytic reactions. So these are the multiple possibilities by which reaction stoichiometry as well as corresponding kinetic parameters can be defined in the simulation environment. The reactive distillation set of reaction is specific to the red flag column. Crystallization reactions are specific to the batch operations, whereas other reactions can be defined for the CSTR, plug flow reactor, batch reactor, or the pressure relief involving the chemical reactions. For this tutorial, we will practice how to define power law reactions and LHHW reactions in Aspen Plus, and then we will simulate CSTR and plug flow reactors. The power law expression can be defined with the reference temperature specification or without reference temperature specification. The general expression is common to most of the reactions. The involved kinetic factors include the rate constant, pre-exponent, temperature exponent, and activation energy. The concentration can be defined in terms of molarity, molality, partial pressure, mass concentration, and etc. Equilibrium constant involved can be defined as a function of temperature, and Aspen Plus uses our default expression of the equilibrium constant as shown here. Let's consider following case study for the exercise of defining power law expressions and power law kinetics in Aspen Plus. Consider ethyl acetate process, where ethanol reacts with the acetic acid in the liquid phase to form ethyl acetate and water through the reaction that is shown here. 1 mole of ethanol reacts with 1 mole of acetic acid to produce 1 mole of ethyl acetate and 1 mole of water. Considering a general expression in terms of reactant A, B and product C and D with the reversible type of reaction, the rate expression is presented as shown here. Here the K is the rate constant, Ke is equilibrium constant and C represents the concentration over here. The rate constant is presented as Arrhenius expression with the pre-exponent factor and activation energy, and for backward reaction equilibrium constant is also provided. The reaction rate is given in the units of kilomole per meter cube per second. So it is asked to define the stoichiometry and reaction kinetics in Aspen Plus. Let's open a new simulation without any default template. Add the components using find search option. Put the search criteria equal to the component name. First component is ethanol. Add this component to the selected components. Add acetic acid. Add ethyl acetate and water. Let's slightly rename the components for better recognition. Put A acid to acetic acid, E acetate to ethyl acetate, and water is fine. Move to the method selection window. Attach an RTL HOC model. Click next. Next. Check the box estimate missing parameters using Unifac model to estimate any missing parameter. The results of the properties environment are available. The chemistry of electrolyte reactions can be defined in the properties environment under chemistry folder. You can define it directly by creating a new reaction, or most of the time using electrolyte wizard for creating the electrolyte chemistry is helpful. For non-electrolyte reactions and corresponding kinetics are defined in the simulation environment under reactions folder. Let's create a new reaction set. Here you can notice that you can select multiple templates for defining the reaction sets. So these are the templates used for defining the reaction stoichiometry and the corresponding kinetics. Many of them for polymerization reactions including Ziegler-Natta, step growth, segment-based polymer pyrolysis. There is a set dedicated for red flag columns to simulate the reactive distillation process. There are options for fermentation reactions or crystallization reactions, polymer emulsions, free radical polymerization reactions, as well as ionic polymerization reactions. Let's explore general reaction set and power law for this exercise. Also create a power law reaction set just to compare the difference between the two. The power law reaction set gives the option to define the stoichiometry, reaction kinetics, equilibrium reaction, and activities are displayed over here. Whereas in the general reaction set, there are multiple other options compared to the power law reaction set. Here you can define the reaction stoichiometry as well as configuration of the reaction, kinetics, equilibrium. You can attach a custom term to the power law for non-standard type of power law reaction kinetics, and there is also option of LHHW in this reaction set. The summary of the kinetic reactions is displayed on this tab as well. For the synthesis of ethyl acetate by reaction of ethanol and acetic acid, the kinetics are of the form of power law including a reversible term. So you have to define the equilibrium constant as well to complete the definition of reversible reaction rate. Let's see the option of defining this reaction in the power law first. Add a new reaction. Here the reaction type can be kinetic or equilibrium. So in case of reversible reaction, where you have to define the kinetics of the forward reaction as well as backward reaction, you have to define two separate reactions, one for the forward reaction and the second for the reverse reaction, since only one of the reaction type can be defined for the given reaction. So let's choose the reactant components and product components. Define the coefficients of the reaction that indicates the number of moles reacting in the stoichiometry. 1 mole of ethanol reacts with 1 mole of acetic acid, the coefficients of the reactants are displayed as minus values and the coefficients of the products are displayed as positive values. The exponent corresponds to the concentration powers in the reaction rate equation. So this reaction can be split into two reactions where the forward reaction rate will be KCACB and the backward rate will be KCCCD over equilibrium constant. And the power raised to the concentration terms is 1 for all the components. So for the forward reaction, the exponent of the reactants will be 1 and the exponents of the products will be 0. That defines the first reaction stoichiometry. Let's define the reverse reaction stoichiometry as well, where ethyl acetate and water will react together to produce ethanol and acetic acid. -1 coefficients for the reactants and positive values for the products. This time the exponent of ethyl acetate is 1 and water is 1, whereas the exponent of the product will be 0. So the stoichiometry of the two reactions is defined. Now we can move to the kinetic section. Here you have to define the reacting phase and the basis of the reaction. It is mentioned that the reaction rate is given in the units of kilomoles per meter cube per second, where the meter cube defines the rate basis. So that is the reactor volume. If reference temperature T0 is specified, then the kinetic factor can be defined like this. Otherwise, Aspen uses this simple formulation to calculate the kinetic factor. Here K is the pre-exponent factor and the value of pre-exponent factor is given as 1.206 into 10 to the power 6 and activation energy is 54,240 kilojoules per kilomole. Let's define these values. So if no information of T0 is given, then you don't need to specify anything over here. Let's add the kinetics of the backward reaction. For the backward reaction, the pre-exponent factor will be the pre-exponent factor defined in the forward reaction rate divided by the equilibrium constant. So the pre-exponent factor for the forward reaction rate is K and the equilibrium constant is, let's say, Ke. Let's calculate the value of the forward rate constant as the pre-exponent factor 1.206 e power 6 multiplied by exponent of minus 54240 divided by R. Let's put 8.314 divided by, for a moment we can use 25 degrees Celsius. So the temperature should correspond to 298 Kelvin. So this is a value for the constant for the forward rate reaction. The equilibrium is 4.5. So the backward rate constant excluding the activation energy should be equal to K divided by equilibrium constant. So the forward rate constant is defined in terms of the pre-exponent factor and activation energy. The backward rate constant can be defined only in terms of the pre-exponent factor and the activation energy value can be put equal to 0. So let's copy this number 8.33 into 10 to the power minus 5 and use it as the backward rate constant. 8.33 e power minus 5 and the activation energy is equal to 0. So the definition of the reaction stoichiometry and kinetic parameters using the reaction set power law is complete. Let's see how to define the same reaction kinetics using general reaction set. Add a new reaction. Here you can notice a reaction class as power law or equilibrium or LHHW or generalized LHHW. Besides, you can notice that you can directly introduce the reaction reversibility while defining the reaction stoichiometry. Let's use the name as RPL. Define the components. Ethanol reacts with acetic acid to produce ethyl acetate and water. The coefficients for the forward reaction is -1 for the reactants and 1 for the product components. Put the reaction as reversible. So while adding the reversible, it immediately opens the folder of equilibrium to define the reaction reversibility or the equilibrium constant. An important difference to notice is in the general reaction set, you can define power law, equilibrium and LHHW type of reactions in the same reaction set, whereas in the other reaction set including power law and LHHW, you can only define the kinetic reaction or equilibrium reaction of the same class in a single set. Let's move to the kinetic tab. Here you need to define the kinetics of the forward reaction. that is 1.206 e power 6 as the pre-exponent factor. The activation energy of the forward rate constant is 54240 kilojoules per kilomole. The reaction phase is liquid, rate basis is the reaction volume, and the units for the reaction rate is kilomoles per cubic meter per second. Next is to define the equilibrium constant. On the same page, you can notice that Aspen Plus allows to calculate the reaction rate based on the driving force expression, where you can compute the reverse rate using default microscopic reversibility, or you can separately define the rate constant and concentration exponents of the forward and backward reactions. For this exercise, let's go to the equilibrium tab and define the magnitude of the equilibrium constant. Aspen Plus allows to calculate the equilibrium constant based on the Gibbs free energy, or you can define the specific value of the equilibrium constant using a general expression of the k values. So here natural log of k equilibrium is equal to the coefficient a plus coefficient b over t and so on. Let's align the value of the equilibrium constant given in the problem statement with this expression. So we have to take the natural log of the k equilibrium value to determine the coefficient a value. So the natural log of k equilibrium is 1.504. That directly defines the value of a coefficient. And the concentration basis for the equilibrium constant is molarity. Now in the kinetic tab, the only missing information is order of the reaction, that is defined as the concentration exponents of the forward reaction rate. The concentration exponent of the forward reaction rate is 1, 1 and 0, 0 for the products. So the definition of the power law rate expression is complete and you are ready to draw the flow sheet and simulate the reactor problem. This is how you can define the power law expressions using a template of power law set or a template general set. Let's save this file for simulation in the later half of this tutorial video. Let's also do an exercise how to define LHHW type of reaction kinetics in Aspen Plus. This is slightly tricky as it involves the calculation of special coefficients as per the format used by Aspen Plus. Langmuir-Hinshelwood-Hougen-Watson type of reaction kinetics are very common for heterogeneous catalyzed reactions where the reaction kinetics and mass transfer plays competitive role in the calculation of overall rate of the reaction. The general expression for LHHW type of kinetics involves the term of kinetic factor, a driving force, and an adsorption term. The driving force expresses concentration-based reversible reaction rates, and the adsorption term indicates the competitive adsorption of the involved species in the heterogeneous catalytic reaction. Let's assume a general reaction of the type where W and X reacts together to form the products Y and Z in the reversible reaction. One of the possible representative of the above general expression can be the kinetic factor in terms of Arrhenius expression, a driving force involving forward rate and the backward rate, and the adsorption term, that is combination of several terms corresponding to the competitive adsorption. Sometimes it is more convenient to use an alternative form of the kinetic reaction where kinetic factor is merged together with the forward and backward rate constants of the driving force. This is particularly important while defining the reaction and kinetics in Aspen Plus, since Aspen Plus assumes that the activation energy of the kinetic factor is positive, so the exponent value have to be negative for the kinetic factor, and it does not matter for the exponent values for the forward and backward rate constants of the driving force. Let's consider a problem to better understand how to determine the coefficients for use with the Aspen Plus LHHW type of reaction kinetics. Consider the conversion of carbon dioxide and hydrogen into methanol according to the following set of reactions. This example is taken from the textbook Aspen Plus Chemical Engineering Applications by Kamal Al-Mala. I suggest to consult this book for further details about this exercise. There are two reactions involved in the production of methanol by reaction of carbon dioxide and hydrogen. First is the main reaction, where 1 mole of carbon dioxide reacts with 3 moles of hydrogen to produce 1 mole of methanol and 1 mole of water. The rate expression in the units of kilomole per kilogram of catalyst per second is expressed in terms of the kinetic factor in the light orange color, driving force in the green color, and the adsorption term in the yellow color. Similarly, the side reaction is the water gas shift reaction, where hydrogen reacts with carbon dioxide to produce carbon monoxide and water. The rate expression for this water gas shift reaction is also expressed in terms of LHHW model. So you are asked to define the stoichiometry of this reaction and kinetics in Aspen Plus. So let's first determine the coefficient values that can be inserted in Aspen Plus to complete the definition of the LHHW model. The most important information in considering the LHHW kinetics in Aspen Plus is the activation energy appearing in the kinetic factor has to be a positive value. That means the exponent should be negative in the kinetic factor. This is true in case of the kinetic expression of the water gas shift reaction, where the exponent is negative, whereas the exponent of the main reaction is positive. That means the activation energy appearing in the kinetic factor of this expression is negative. That is not acceptable by Aspen Plus. So the alternative way is to merge the value of the kinetic factor with the driving force and define the kinetic factor as 1. So the rate expression by merging the kinetic factor with the driving force of the main reaction is like this. The forward rate constant of the driving force is obtained by multiplying the kinetic factor with the forward rate constant, and the backward rate constant is also shifted because of the multiplication of the kinetic factor with the original backward rate constant. Still, Aspen Plus will use the same Arrhenius type of expression for the kinetic factor. To translate the value of 1 into the Arrhenius expression, you have to use the pre-exponent factor K as 1, temperature exponent as 0, and activation energy as 0. So that gives the value equal to 1. So Aspen Plus requires these 3 values to define the kinetic factor. In case of driving force, each term is defined separately. So the first term in the driving force is this one, and the second term in the driving force is this one. The powers of the concentrations as partial pressures in this case are defined separately as the concentration exponents, and the pre-exponent to the concentrations is defined separately using a generic expression as of equilibrium constant defined earlier. So the generic expression to define the coefficients is natural log of the K value equals A coefficient plus B coefficient over temperature plus C coefficient and so on. Let's translate the pre-exponents as of the format of Aspen Plus, where the natural log of forward rate coefficient is natural log of this vector that splits the multiplying terms into the sum of the two terms. Natural log of 1.07 in 10 to the power minus 13, and natural log of the exponent is simply the factor appearing in the exponent. That gives a correspondence to the general expression of A equivalent to natural log of 1.07 in 10 to the power minus 13, that is equal to minus 29.86, and correspondence to the second term to the general expression of B over T, where B is equal to the factor appearing in the numerator of the exponent term, that is 4413.76. Since there is no term after the exponent factor, those will be considered as zeros. So the Aspen Plus requires the definition of A, B, C and D coefficients to define the driving force as well as the concentration exponents. Concentration exponents are the exponents of the partial pressures multiplying with the kinetic factor. The exponent of carbon dioxide is 1, exponent of hydrogen is 1, and no other concentration term appears for the forward rate, so those will be zeros. So the exponents for CO2 and hydrogen are 1, and methanol and water are zeros. Similarly, the second term for the driving force will be backward rate. Natural log of 4.182 into 10 to the power 7 will be the value of the coefficient A, and numerator of the exponent will be the value of coefficient B. In the absence of other terms, the coefficient C and D will be zeros. The exponent of methanol and water are 1, and the exponent of hydrogen is -2 because it appears in the denominator. No other term appears in the backward rate, so the exponent of CO2 will be 0. Similarly, you need to define the concentration exponents and the coefficients A, B, C and D for the adsorption term as well. In the denominator, you can notice 4 different terms separated by plus sign. So all these terms will have separate values for the coefficients as well as the concentration exponents. The way they are defined in the Aspen Plus is the matrix representation. Matrix representation for the concentration exponents and the matrix representations for the adsorption coefficients. So this adsorption term can be rewritten in terms of the constant multiplied by the concentrations. First term is equal to 1 and that means it can be written as 1 multiplied by the concentration raised to the powers of order of reaction. Similarly, the second term can be written as the constant term multiplied by the concentrations raised to the powers of orders of those terms, and so on. The concentrations exponents for term 1 are 0 for both of these, hydrogen and water. For the second term, it is -1 for the hydrogen and +1 for the water. For the third term, it's 0.5 for hydrogen and 0 for water. For the fourth term, it's 0 for hydrogen and 1 for water. So that defines a matrix of the concentration exponents. The coefficients are calculated as we have discussed previously for the driving force. For the term 1, constant is 1, so the coefficient A will be the natural log of 1, and in the absence of other terms, the coefficients B, C and D will be zeros. For second term, the coefficient will be natural log of 3453.38 and other terms will be 0. For third term, the coefficient will be natural log of 1.578 into 10 to the power -3 for A coefficient and 2068.44, that is numerator of the exponent, is the coefficient B. And similarly, the coefficients for the term 4. Same way you can determine the required information for water gas shift reaction. So let's define these coefficients and the kinetics in Aspen Plus. Open a new simulation file without defining any default template. Define the components as CO2, H2, methanol, CO and H2O. Proceed to the method section. Let's use SRK as an appropriate method for this simulation. Proceed to the parameters. Let's estimate all the missing parameters using UNIFAC. So the required information is available. However, with the warning, let's check the warning. So the SRK requires a different method for the calculation of free water, that is STEAM and BS. On the method section, let's change the free water calculation method from STEAM TA to STEAM and BS. Rerun the simulation. So results are available. Let's move to the simulation environment. Here we need to create LHHW type of reaction in the reaction section. Let's create a new reaction set. Choose it from either general set or LHHW set. Create a reaction. Let's open the Word document in parallel to define the reaction stoichiometry and the kinetic parameters. Here the first reaction is reaction between carbon dioxide and hydrogen to produce methanol and water. 1 mole of carbon dioxide reacts with 3 moles of hydrogen to produce 1 mole of methanol and 1 mole of water. It's a kinetic reaction, so choose the reaction type as kinetic. First reaction stoichiometry is complete. Let's define the kinetics first and then we will add the second reaction. It's a catalytic gas phase reaction. Let's close this navigation pan for better view. So the reacting phase is vapors. Rate bases are catalyst weight. Kinetic factor for the first reaction is calculated as K equal to 1, N equals 0 and E equals 0. So put K equals 1, N is defined as default, put E equals 0. So the first term as the kinetic factor is complete. Now we can define the driving force expression. For that, click driving force. Basis for the concentration is partial pressure. Other possible options are molarity, molar mass fractions, mass concentrations. Even you can define as gamma and fugacity. Let's choose partial pressure. Here we need to define both of the terms, including concentration exponents and the coefficients. The concentration exponents for the first term of the driving force, that is the forward rate, where carbon dioxide exponent is 1, hydrogen exponent is 1 and methanol and water exponents are 0. So put the exponents of carbon dioxide and hydrogen as 1 and methanol and water as 0. The coefficient A is minus 29.86 and the coefficient B is 4413.76. Define the parameters of the second term where the exponents of hydrogen is minus 2, methanol 1 and water as 1. So define the exponents for carbon dioxide is 0, hydrogen minus 2, methanol 1 and water is 1. Coefficients are 17.54 for A coefficient, minus 2645.96 for coefficient B. So C and D coefficients are 0. So the driving force has been defined. Now we need to define the adsorption terms. For the adsorption term, there are two components appearing in the concentration exponents. Let's add hydrogen as a first component and water as a second component. There are four terms. The concentration exponents for the term 1 are 0, term 2 is minus 1 and 1, term 3 is 0.5 and 0, and term 4 is 0 and 1. The adsorption expression exponent is the power of the denominator in the rate expression, that is the factor given over here. So the adsorption expression exponent for the methanol synthesis reaction is 3. Now we need to define the adsorption coefficients, that is a matrix of 4 terms by 4 coefficients. Let's add all the terms first. 1, term number 2, term number 3 and term number 4. To complete the matrix, you can also copy all the coefficient values from the table and simply paste in the table of adsorption coefficients. That's it. The adsorption expression has been defined, and with this, the stoichiometry and the kinetic factors of the LHHW model of methanol synthesis are complete. Similarly, you can define the stoichiometry and kinetics of the water gas shift reaction. So both of these reactions has been defined. Let's save this file for use in the later part of this video. Once you are fully aware of defining the reaction kinetics, then you can continue with specifying the appropriate reactor model and simulate the cases. For this video, we will only focus on continuous stir tank reactor and plug flow reactor. In Aspen Plus version 14, the CSTR can be simulated as a shortcut reactor as well as a rigorous reactor involving the possibilities to model the heat transfer for heating and cooling requirements. The CSTR can be simulated as an isothermal reactor or can be simulated as adiabatic reactor. Single phase, two phase and 3-phase flash types are available. Geometry of the reactor can be horizontal as well as vertical. You have the option to define the vessel head type as well as details of the agitator. The possible options of the heat transfer specifications include the jacket type heat transfer and the coils type heat transfer to meet heating and cooling requirements of the reactor. Let's consider this problem statement and then we'll move on to Aspen Plus for the simulation of CSTR. Consider the same case of ethyl acetate process where ethanol reacts with acetic acid to produce ethyl acetate in the liquid phase. We have already defined the reaction stoichiometry and the kinetics in Aspen Plus file. The operating conditions include the reaction at 50 degrees Celsius and 101 kilopascal pressure, the feed streams having ethanol and acetic acid flowing at a rate of 50 kilomoles per hour at 20 degrees Celsius and 110 kilopascal enters the reactor. The reactor volume is 3 meter cube. So for these situations, you are asked to calculate the product composition, heat duty and reaction conversion. So let's open Aspen Plus and simulate the case. Use the same file as we defined in the first exercise of this tutorial. Here is the Aspen Plus file where we have defined the reversible reaction between ethanol and acetic acid to produce ethyl acetate and water. The stoichiometry and kinetics are defined as power law using general set template and power law template. Let's define the flow sheet. Choose a continuous stir tank reactor from the reactors palette. In the previous video, we have learned how to simulate first 4 reactors of this model palette where stoichiometric reactor and yield reactor are balance-based reactors and equilibrium reactor and Gibbs reactor are equilibrium reactors. So rest of these 4 reactors are the kinetic reactors. Choose RCSTR, attach a material stream for ethanol, attach another material stream for acetic acid and a product stream. Rename the streams as ethanol, acetic acid and product. Rename the block as RCSTR. Let's define the ethanol stream where the ethanol enters at 25 degrees Celsius and 110 kilopascal. The flow rate of ethanol is said to have a value of 50 kilomoles per hour. Similarly, in the acetic acid stream, temperature is 25 degrees Celsius, pressure is 110 kilopascal and the flow rate of acetic acid is the same 50 kilomoles per hour. The feed streams are complete. So let's move to the specifications of RCSTR. Hide this model palette to have a more space for the working window. Here you have the 2 major options as model fidelity for the RCSTR. The first one is the conceptual mode where heat transfer calculation is based on the shortcut method where only duty corresponding to the reactions is calculated and displayed in the results. The other option is equipment based model where rigorous heat transfer calculation is performed for jackets as well as for coil type heating cooling purposes. Besides, you have the option to define the geometry and the parameters for the heat transfer calculations. While entering into the rigorous model, you can notice vessel tab has been activated as well as heat transfer tab has been activated, and those are inactive in case of shortcut simulation. In the rigorous calculations, besides defining the kinetics, you can notice that you can specify the geometry as a vertical vessel or a horizontal vessel. In both of these cases, you can define pot head as elliptical, conical, flat, hemispherical or toruspherical for the top and bottom in case of vertical, and only the top, that is actually the sides, for the horizontal vessel. Size of the vessel can be defined in terms of diameter and tangent to tangent length. Tangent to tangent length is the length of the constant diameter vessel excluding the pot heads. Otherwise, it can be defined as diameter and volume of the vessel or tangent to tangent length and the volume of the vessel. There is also an option to define a utility streams as heating and cooling stream to meet the desired heat duty of the reactions. This is possible if you have defined a utility stream in the flow sheet. You can also define the catalyst in case the solid catalyst is present for heterogeneous catalytic reactions. In the heat transfer tab, you can use a jacket type heating and cooling mechanism or coil type heating and cooling mechanism. Let's put the geometry into the vertical arrangement for better visualization. It is possible to simulate a jacketed CSTR while placing jacket at the bottom as well or excluding it. Alternatively, you can place a coil around or inside the CSTR vessel. You can define the relevant geometrical details of the jacket as well as the coils. Besides, there is an option to determine the heat loss between the environment and the vessel. For that purpose, you can define the ambient temperature as well as overall heat transfer coefficient. In the jacket and coils tab, you can define the details by which the heat transfer coefficient will be calculated. Either you can specify a fixed value of heat transfer coefficient, or you can separately compute the heat transfer coefficients for the process side as well as for the service side. There is an option to define the film coefficient directly as a scalar value. Similarly, the process side film heat transfer coefficient can be defined as a scalar value, or they can be computed by Seidel-Tate correlation with the help of material properties, dimensionless numbers, and the coefficients. Also, there is an option to include the agitator diameter and the rotational speed. For the service side, the same correlations can be used for the calculation of film heat transfer coefficient, where the properties of the heating and cooling utility can be given, as well as parameters for the calculation of dimensionless numbers can be provided for the calculation of film heat transfer coefficient. This gives an extensive details for the calculation of heat transfer while using a rigorous or equipment based model of the CSTR. For the given case, we'll stick to the conceptual mode since no details of the heat transfer calculations is required or the vessel geometry definition is required. Simply the operating pressure is provided as 101 kilopascal. Temperature is mentioned as 50 degrees Celsius. The valid phase for the reaction is only liquid, and we are given with the 3 cubic meter volume of the reactor. Beside this specification, if you are using adiabatic CSTR, then you can put a duty equal to 0. So any heat of reaction will participate in the temperature change. There is an also option to consider the mass transfer limitations if the reaction kinetics may be co-limited by the kinetics as well as the mass transfer because of the poor mixing inside the vessel. Then you can define the mass transfer in terms of the component volumetric mass transfer coefficients. Let's skip this as of now and move to the kinetics tab and attach the reaction set to this vessel. The CSTR model can be used as a stir tank reactor for simple reactions as well as for crystallization reactions or fermentation reactions. In case of crystallization, the details of the agitator can be defined in terms of the impeller tip rotation, impeller diameter, and power number. This is also an option to uncheck the reaction. So no reaction will be attached to this vessel, and vessel can be used a simple mixer without any reaction taking place inside the vessel. To include a reaction, transfer the reaction set from the available to the selected side, and that completes the specifications of the CSTR, and the simulation is ready to run and view the results. Let's save this file and run the simulation. So results are available without any warning or error. To view the results, go to the results section where all the details about the block are given, including heat duty, volume of the reactor, residence time. So with the given kinetics, the residence time is 30.36 minutes. You can also check the reaction kinetics where the net reaction rate is given along with the kinetic factor and the driving force. You can also check the component consumption and generation rates in terms of mole rates as well as mass rates. Let's see the stream results. Here the reaction temperature of the feed streams and the product stream is given. The reaction pressure is defined and the phase of the inlet and outlet streams is also defined. Let's go to the molar composition. 50 moles of ethanol and 50 moles of acetic acid react to produce 32.89 moles of ethyl acetate and the same number of moles of the water. As per this reaction, the conversion is 50 minus 17.10 divided by 50. Let's calculate how much this conversion is. So the conversion X is 50 minus 17.10 divided by 50. So the conversion with given conditions is close to 65%. So this is how you can define the kinetics and attach the kinetics to continuous stir tank reactor for the simulation, view the heat duty, reaction conversion, and other details calculated from the CSTR simulation. Besides CSTR, let's see how to define the specifications of the plug flow reactor and simulate for the methanol synthesis reaction as kinetics are defined earlier. For the plug flow reactor, the reactor can be simulated with a fixed operating temperature, or it can be simulated as adiabatic reactor, or other utility streams can be attached to the reactor, and the utility flow on co-current or counter-current flow scheme can be simulated. The Fallot phases are the same as single phase vapor or liquid, two-phase system as vapor liquid system, and three phases can be simulated with the plug flow reactor. Geometry of the model can be defined as a single tube, a catalytic fixed bed reactor, multi-tubular reactor, a single tube with a variable diameter, or the geometry can be inclined to a certain angle specifically for the pressure drop calculations. Besides these details, the plug flow reactor model also provides the option to specify the details of the solid catalyst and use the available pressure drop correlation models. Let's use the problem statement of methanol synthesis and see how to specify the plug flow reactor for the simulation of this specific reaction case. For reactor simulation, a feed stream containing carbon monoxide, hydrogen and carbon dioxide with the flow rates as mentioned here enters the reactor at 150 degrees Celsius and 110 bar pressure. The reaction occurs in a multi-tubular catalytic fixed bed reactor with following specifications. Number of tubes in the reactor are 8000. Reactor length is mentioned as 12.2 meter and the diameter of a single tube is 0.0375 meter. The bed porosity is 50%. Catalytic particle density is 2000 kilogram per meter cube. And for the heat transfer calculations, a temperature profile inside the reactor is defined. The inlet temperature of the reactor is 150 degrees Celsius. The outlet temperature is 260 degrees Celsius. And the temperature at a 90% length from the inlet is given as 280 degrees Celsius. So with these details, you are asked to calculate the heat duty, residence time, and the reactant conversion. Let's open the same file where kinetics of methanol synthesis and water gas shift reaction has been defined as LHHW type of kinetic model. So here the reaction kinetics are defined as LHHW type of kinetics. Let's first draw the flow sheet. Choose a plug flow reactor model. You can choose any of these available icons. Attach an inlet material stream as well as outlet material stream. There is an option to attach a thermal fluid to ensure the desired operating temperature inside the plug flow reactor. For the given exercise, since temperature profile is known, we can directly enter the temperature profile and calculate the heat duty. Otherwise, a utility stream can be attached through a thermal fluid connection ports and calculations can be performed accordingly. Let's rename the feed stream as feed and product stream as product and rename the reactor as RPLUG. Control A and Control B. Move to the feed specifications where the temperature is defined as 150 degrees Celsius and pressure is 110 bar. Flow rate of carbon monoxide is 4066 kilomoles per hour. Hydrogen flow is 28920 kilomoles per hour and carbon dioxide flow rate is 3976 kilomoles per hour. Let's define these flow rates directly in the composition section. So the flow rates are defined. Let's move to the specifications of the reactor model. In the reactor model, first you need to select the type of the reactor and that is specifically associated to heat transfer profiles of the reactor. Either you can define a specified reactor temperature. For that specification, it is possible to define a constant inlet temperature as of the feed temperature, or there can be a complete isothermal case where a specified reactor temperature can be defined throughout the reactor length, or there is an option to define a temperature profile along the reactor length. Other options for the reactor type are adiabatic reactor or a constant thermal fluid temperature. If the thermal fluid streams are attached to the plug flow reactor model in the flow sheet, then it is possible to simulate it as a co-current flow case or counter-current flow case. Besides, a thermal fluid temperature profile can be defined or a specified external heat flux profile can be defined. These are the multiple simulation options. For the given case, since the specified temperature profile is defined, where at the start of the reactor temperature is 150 degrees Celsius, at 90% length that can be defined as a fraction 0.9, the temperature is 280 degrees Celsius, and at the exit of the reactor, temperature is defined as 267 degrees Celsius. Next, you need to define the configuration of the reactor. Either it can be a single tube fixed bed reactor, or it can be defined as a multi-tubular reactor. For the given case, number of tubes were 8000. Otherwise, it can be defined as a variable diameter tubular reactor, where the diameter changes can be defined in the diameter tab. A known diameter can be defined at desired length of the reactor. Let's define the reactor tube dimensions. Length of the reactor is 12.2 meter and the diameter is 0.0375 meter. It is possible to change the elevation or angle of the reactor. This is particularly relevant for the pressure drop calculations, and this option is activated once a pressure drop correlation is defined in the pressures tab. You can choose the phase between a single phase, two phase and three phase systems. For the given case, let's go with the vapor only. Go to the reactions tab. You can attach a reaction for the simulation of the chemistry. Otherwise, you can uncheck the reactor system. In that case, RPLUG model will be used for the simulation of fluid dynamics, where a catalyst can be defined as a fixed bed and pressure drop calculations can be performed without any involved reaction. Let's use it as a reactive system. Go to the catalyst tab for the specifications of the catalyst. The catalyst specifications can be provided in the form of bed porosity. The other specifications can be catalyst loading or particle density. In given case, the particle density of 2000 kg per cubic meter is mentioned. Besides, you can consider ignoring catalyst volume in the rate residence time calculations as well. It is also possible to define the particle geometry for the calculations of the pressure drop if appropriate pressure drop correlation is selected. The pressure drop correlation can be selected in the pressures tab. By default, you can provide a numerical value for the pressure drop across the reactor length, or you can choose from the available pressure drop correlations. The available pressure drop correlations include Beck-Sprell model, well-known Darcy's law, Ergun equation, HTFS model, and bunch of other pressure drop correlations. For convenience, let's choose Ergun equation. Besides, there is also an option to associate a reactor holdup using a holdup correlation or a fraction profile along the reactor. Let's proceed with the default specification of no slip between the phases. All the specifications are complete, so we are ready to run the simulation. Let's run the simulation and the results are available. Let's proceed to the results section. Here you can notice the heat duty in megawatts, the residence time in seconds, it's 13.909 seconds. You can check the profiles of various parameters including compositions, temperature, pressure, heat duty, residence time. Let's see how temperature is changing along the length of the reactor. So the temperature almost linearly grows to a maximum of 280 degrees Celsius that is specified. So while specifying the temperature profile in the reactor, Aspen Plus assumes a linear interpolation between the specified values and performs the reaction and heat transfer calculations. Let's have a look on the reaction kinetics. The net reaction rate is given. Driving force and adsorption terms are also provided for reaction 1 as well as for reaction 2. Component generation rates are also displayed, where the generation rates in terms of kilomoles per hour per meter length of the reactor are given. Let's have a look on the stream results. You can notice feed and product temperatures, pressure. So using default parameters and Ergun equation, only a slight temperature drop is calculated. The reaction phase is vapor. Let's proceed with the molar compositions. The inlet flow rate of carbon dioxide is 3976 kilomoles per hour, out of which 3125.7 kilomoles per hour leaves unreacted. Conversion can be calculated as equal to 3976 minus CO2 at the exit of the reactor 3125.74 divided by at the inlet 3976. So the conversion of carbon dioxide is almost 21.4%. You can also read other results of the interest from the stream summary as well as from the profiles as well as from the results section. This is how you can simulate plug flow reactor using reaction of any relevant kinetic model. In this video, we have learned how to define different type of reaction kinetics and simulate continuous stir tank reactor and plug flow reactor in Aspen Plus version 14. In the next video, we will learn how to simulate batch reactor and water electrolysis reactor, and also learn how to simulate the reactor models specifically when a recycle stream is connected.